Here's yet another example problem to investigate force of friction. So we're shown that there's a metal desk, and on top of that metal desk sits a wood block that we've labeled as mass number 2, and on top of that wood block is a plastic block that we've named M1, and then a string connects from block 2 to block number 3, which is made out of stone, and the whole system's released from rest. So you can see we're given all of the masses of the 3 plastic, wood, and stone blocks. We're also given a couple of coefficients of friction. We're given a coefficient of static friction and a coefficient of kinetic friction. Now, that represents the coefficient of friction for wood on metal. Something interesting about coefficients of friction is you always have to name 2 materials in order to have a reasonable coefficient of friction. In other words, it would be unreasonable to ask, what's the coefficient of friction of wood? It just doesn't make sense, right? But there's a coefficient of friction for wood rubbing across metal. There's no such thing as a coefficient of friction for glass, but there is a coefficient of friction for cotton on glass, and so on and so forth. So we're given the coefficient of friction that represents how rough that combination of surfaces is. Now you can imagine when the system is released from rest and accelerates in this direction, if it accelerates enough, it could be like pulling the tablecloth out from under the dishes. If the plastic block is at rest, and the whole system is released from rest, but consider the inertia of the plastic block. Because the string is only connected to block number 2, then block 2 might slide out from underneath block 1. There must be some amount of friction between plastic and wood that allows the system to accelerate together, and that becomes the question in this problem, right? Coefficient of static friction for plastic on wood. What's the minimum required value so that the system accelerates together as one combined object? So first of all, let's determine what the acceleration of the whole system is. Actually, you know what? Even though the numerical values are given, let's try to solve the problem without giving any numerical values. We can plug them all in the end. Let's see if we can derive an algebraic expression that'll give us the minimum required coefficient of static friction between the plastic and the wood. Okay, so let's see. We make a free body diagram for the stone. That came out funny. So say this is M3G. There's tension. Let's make a free body diagram for the plastic and the wood together as one object. So pulling to the right is the same tension that's pulling upward on block number 3. Now there's a couple of normal forces. There's the normal force of contact between the plastic and the wood, but because we're making a free body diagram for the 2 of those combined, that's an internal force. External is the normal force at the desk. So there we go. We'll call that N subscript D, normal force of the desk. And then downward is the combined mass, M1 plus M2 quantity times G. And then back in this direction is some force of kinetic friction. So how do I know it's kinetic? Well, the problem implied that the system's going to be accelerating. So I guess we should check and see if that's the case. Maybe this is a force of kinetic or force of static, and we're not sure. Okay, so let's just go with this. The forces in opposite directions on the y-axis will cancel out, and so our net force is equal to tension minus force of friction. Whether that's static or kinetic, we're about to find out. But this becomes M1 plus M2 quantity times A is equal to T minus force of friction. Okay, and then the other free body diagram for the stone, let's see, M3G minus T equals M3A. I found the trick to these sort of problems is to add them together. I guess I should transpose this then. Okay, positive t and negative t cancel out. A times the quantity m1 plus m2 plus m3 is equal to m3g minus force of friction. Okay, force of friction, well, that's the same thing as mu times normal force. Now let's see, where did that force of friction come from? It was here, where the normal force along the positive y-axis has to cancel out m1 plus m2 quantity times g along the negative y-axis. So we can make that substitution. So A times the mass of the whole system, m1 plus m2 plus m3, is equal to m3g minus mu times quantity m1 plus m2 times g, mu times normal force. All right, well, let's see here. m3 times g, that's 4 kilograms for m3, and g is 9.8. Yeah. Well, let's just simplify this a little bit. A is equal to g times the quantity m3 minus m1 plus m2 added together multiplied by mu. And this is all divided by m1 plus m2 plus m3. So the bottom line here is if the numerator is equal to 0, that's the only way the acceleration could be 0. So is the numerator going to be 0? Well, I can plug in values here then, right? We're just looking at the quantity in the numerator, m3 minus mu times m1 plus m2. So the problem gave us that m3 is equal to 4 kilograms. m1 plus m2, let's see, that was 2 kilograms plus 5 kilograms, so that would be 7. So 4 minus mu times 7. And the coefficient of static friction was given as 0.5 and kinetic was 0.4. So even with a force of static friction, 0.5 times 7 would give us 3.5. Yeah, so the numerator is non-zero, which means there is indeed an acceleration. Not even the static friction is enough to keep it at rest. Okay, and because it's not at rest then, going forward, we're interested in the coefficient of kinetic friction. So we've done it. We've derived an equation for the acceleration of the system. That's a good halfway point in this problem. Now the remainder of the problem then is to figure out what's the required coefficient of static friction between the plastic and the wood so that the wooden block doesn't slide out from underneath the plastic block, so that they grip and slide together as one. So now what we want to do is make a free body diagram just for block number 1. So that would look like this. It weighs something, yeah, so M1G pulls down. Now let's see, oh well, there's a contact force pushing up. I won't call this N subscript desk, maybe we'll call it N prime, a different normal force, right? It's not the desk pushing up on the 2 blocks, it's the lower block pushing up on the upper block. Let's see, tension does not act on this free body diagram. The tension is applied to block number 2, but there is no string connected to block number 1, so there's no tension to draw. What about friction? Yeah, there's friction. Now, the whole system is going to accelerate this way, so I can understand how some people might think the friction pulls back this way. The idea of friction is that it's a force that opposes motion. But what we should really say is opposes relative motion. If the idea is mass number 2 is getting accelerated in this direction, if block 1 stayed at rest, then the relative motion between the two is block number 2 is trying to go to the right, and relative to block number 2, it's as if block number 1 is trying to go to the left, right? There's 2 different frames of reference. There's somebody fixed with the desk reference frame, and also what if somebody was fixed in the reference frame of the moving block number 2. So in fact, if the whole system does accelerate together as one combined system without any slippage, there must be something propelling block number 1 to the right along with all the other blocks. But it's definitely not the tension in the string, because that tension is not connected to block number 1. So it's actually the grip, the roughness, this static friction between block number 1 and block number 2. Yeah, so this is a force of static friction that's actually going in the direction of the acceleration of the system. This is a case where friction causes the motion. All right, so we know the normal force and mg must cancel each other out, and so if this is the only remaining force, then the net force expressed by this free body diagram is equal to the force of static friction. So this means m1a is equal to mu times normal force prime. So m1a is equal to mu times m1g. We can cancel out the m1. So a is equal to mu g. So mu is equal to a divided by g. And so in this case, we already found an expression for a. So the value of mu that's required is everything in our previous expression with the value of g factored out. So it's m3 minus the quantity m1 plus m2 I missed a mu in there, minus mu times m1 plus m2 all divided by m1 plus m2 plus m3. Now which mu is this? This is mu kinetic between the desk and the wooden block, which in our example had a value of 0.4. Thanks for watching.